We're the field research station of the Science Museum of Minnesota, and myself and my other colleagues there, probably the theme to most of the research questions that we work on is change over time. We try to understand why systems change over time, how they change, and what causes it, which makes this, let me see if this is working here. That's gopher losing percentage over time, and I put it up there because it's a real trend, it's statistically significant, and we all have an opinion on why gopher losing percentage may change over time. But in science, our job is to separate real versus speculation. And so flow, river flow, suspended sediment loads, just like football, have trends over time. There are things that we can correlate and try to describe where they are, but our job is to separate real versus speculation. And that's what I'm going to do today. And so I'm both going to try to present information about how flow and suspended sediment has changed over time, but also the process by which we evaluate the data, the way we look at it, the way we critique it, and arrive at the conclusions and interpretations that we do. And so that's why I put that up there. There's another piece of information regarding reality that is very relevant to Minnesota, and it's depicted in this picture. And while you're reading what's up there, I want to thank my colleagues who worked on this, some of who are here today. Jason Ulrich, who's the co-author on the paper that we just published and is really the wizard behind the math and statistics that we do, is here in the front. And Rick Moore, who's at University of Minnesota Mankato State, is here and did a lot of the GIS work for us. And I have several other people who have worked on this, and our work was funded both by LCCMR and EPA 319 grants. Do you guys know what's depicted in that picture? Anyone know what's going on there? That's right. That is the moment in time when Ulf Ullman and his son, while grubbing trees out of a new field up not too far from Alexandria, found this stone embedded in the roots of that tree, and it had the inscription on it there that you read in the previous slide. And the interpretation from that stone is that it was carved by Vikings who were traveling through the Great Lakes and across Minnesota, and then subsequently encountered some difficulties and buried this stone. And it is debated whether that stone is real or not. How many people think that the Kensington, first of all, how many people, I'm always curious about this, how many people in the room are familiar with the Kensington runestone? Yeah, most everybody. I used this, by the way, at a talk for a Pheasants Forever meeting, and I incorporated it in a different way, and it was a national audience, and outside of Minnesota, nobody knows what the Kensington runestone is. So, how many people think the runestone is real? Raise your hands. Come on, you raise them up if you think it's real. Okay, yeah, all right. I'm not going to tell you. I'll tell you at the end. But I do it because, oh, it's green now. Yeah, good. The exercise in evaluating whether or not the runestone is real or not is the same as the exercise in evaluating any piece of scientific data. We have observations, we collect evidence, and then from that we draw an interpretation, and from that interpretation there's a response. And that's what I'll lead through today in today's talk regarding sediment and flow. So excess suspended sediment, that's what leads us to work on this problem. Suspended sediment in the rivers is a serious problem, mainly due to turbidity, which affects both fish habitat, water quality for recreation, and submerged aquatic vegetation, which changes the whole ecology for things like ducks and so on. This is the confluence of the Mississippi and St. Croix rivers near Prescott. Obviously, one river is dirty, one river is clean. And most of the sediment that you see here in the Mississippi River, 80% of it comes from the Minnesota River Basin. And I think it's emblematic of the issues that we're facing. And this river subsequently flows into Lake Pepin, which is a natural impoundment on the Mississippi River, collecting water from the St. Croix, Minnesota, and Mississippi watersheds. And we can go into Lake Pepin and take sediment cores and reconstruct how sediment has changed over time. And you've probably heard a lot about Lake Pepin. It's made the news, both newspapers and TV media over the last couple of years, and it's talked about what's happening in Lake Pepin and that it's filling in, and 80% of the sediments from the Minnesota River, and how bad it is, how poor the water quality is. And I just want to state something that from our perspective, it isn't that Lake Pepin is so important. This is the part that gets left out in the media stories every time. We as scientists study Lake Pepin not because it's the most precious lake in the state. It's not more precious than Mille Lacs or Lake of the Woods or Lake Minnetonka. It's that it's a very, very unique lake in the world. It is a natural riverine lake on a very large river system. Because it is a natural impoundment, it has collected sediment since its formation 14,000 years ago, and those sediments can be cored, dated, and interpreted. Lakes, there are only a few lakes in the world that are like that. And Lake Pepin's ability to provide interpretation is for how land use has changed in a region where new settlements have come in and converted the land for agriculture. And that's the story that Lake Pepin tells. And that's why we go and work on Lake Pepin. So when you see that brought up and they mention the St. Croix Research Station, University of Minnesota, it isn't that we're trying to promote Lake Pepin. It's that it's an extremely unique system for us to interpret. And this is what, when we took, so back in both 1996 and 2007, we took 25 cores from Lake Pepin. We date them, we calculate the sediment accumulation history, and if we put all of those cores together, this is what it would look like. This is the change in the sediment flux through Lake Pepin since just prior to European settlement and after European settlement. And what you see is that the sediment accumulation rate in the lake is about almost 10 times faster now than it was prior to European settlement. And that tells us that the lake is going to fill in about 10 times faster, and the lake has always been filling in. It was going to be filled in 3,000 years, and it's now going to be filled in about 350 years. But what's really interesting to us is why does it change in the way that it does? If we had drawn up what we had expected this profile to look like before taking the cores, this is not how we would have drawn it. It should have gone up and then sort of stayed constant. But it goes up and it keeps going up, and maybe it's changing again now. It's a little hard to tell. So the question we ask is, why does it change the way it does? And is it telling us something about the source of eroded sediments to the lake? And this is really important because we can't solve sediment and turbidity issues unless we understand why they change. Unless we know what kind of BMPs to put on the landscape and where, we can't solve the problem. And early on, it became apparent that we had to look at the sources of sediment, and we evaluated those using radioisotopes, cesium and lead-210 and beryllium-10. And I won't go into all of that, but those isotopes allow us to fingerprint different sources of sediment. And the critical designation that we can make is between field eroded sediments, which is where we had traditionally thought was driving this profile. You know, you clear the prairies, you have bare soils for a portion of the year for row cropping, those are erodible soils, and they wash into the rivers and they end up in the lake. But these features, bluffs and stream banks, are also eroding. They're immediately adjacent to the river, and when they fall in, that sediment is carried away. They must be important also. And so using sediment fingerprinting, we were able to look at and distinguish between the contributions from field and non-field erosion sources. And non-field is ravines, stream banks, gullies, those near channel sources. And those are natural features eroding along the lake, or eroding along the rivers. Whoops, sorry. But what we see, this is the amount of sediment. In that previous profile, I've just separated out. This is the amount of sediment just from stream banks, bluffs, and ravines. And what you see, this is the amount prior to European settlement, and it goes up, up, and up. And currently, the amount of sediment eroded from stream banks is about 2/3, 75% of all of the sediment entering the lake. And it has increased 5-fold over time. So the erosion from these kinds of features has increased 5-fold over time and is now the dominant source of sediment to Lake Pepin and the river system. It's not field erosion. And that tells us something really important. It tells us that natural sources are eroding at an unnatural rate. And that's why I put Chuck Norris here. My wife hates Chuck Norris. But I tell her, when you really want to make an important point, you use a bare-chested man doing a leg kick. So when you see Chuck Norris, you saw it on the other Pepin slide, and you see it now, you know it's an important point. This is really key because it drives in the next question is, have our rivers become more erosive over time? And if so, why? And this is a paradigm shift in thinking about erosion. Remember, the old theory was, and even still currently in terms of our management practices, it's that sediment comes from the fields, we've got to keep it on the fields. And what we now realize is that a lot of sediment isn't from the fields, it's from natural sources eroding at an unnatural rate, which begs the question, why? And it almost certainly means that our rivers have become more erosive. So why has non-field erosion increased over time? These are the questions now that we want to answer. Is it due to more precipitation? Is it land use change? Is it drainage? The question is how have these combined to make more erosive rivers? And I put it on the backdrop of this is a Google image of an area south of Mankato, and all these white lines are artificial drainage on the landscape. And here you see pattern tiling. Here's a drained wetland. This is a ditch. Here are the tile mains. They show up. And the other thing you'll notice, and I wanted to point out here, is that I'm going to use the term artificial drainage. Artificial drainage is not interchangeable with the word pattern tiling. Artificial drainage is all of the forms by which we remove water artificially from the landscape, of which pattern tiling is one of those. And in the study today that I'm showing you, that's what we are evaluating. So how have these combined to increase flow in the rivers and make them more erosive? The study then that we undertook was to look at changes in hydrology in 21 watersheds throughout the agricultural regions of the state and look to see if they become more erosive. And we chose these 21 watersheds because they are watersheds that have flow monitoring records going back to 1940. We have no rivers with flow monitoring records before 1940. There's a few with 1938, but nothing that's longer than that. So these were selected simply because it's the best available data set to us. And it's a comparative study. By looking at how different watersheds change, we're able to normalize out some of the parameters. If we looked at a single watershed, it might tell us a different story. But putting them all together and having the comparison should help us to tease apart the role of climate, drainage, crop conversion, urbanization, etc. The first question that we have to answer is, has flow changed? If flow has not gone up in the rivers, we're not going to be able to say, or it's going to be very difficult to say that the rivers have been more erosive. So the first most basic parameter that we analyzed was river flow. And river flow, because this is a comparative study, is a variation of watershed size. Big watersheds have more flow than small watersheds. So to correct for that, we divide river flow by watershed area, and that gives us water yield. So today you'll see some times where I use the term water yield, or the water yield will be in the graphs. Just think flow in your mind. It's the same thing, but it's been corrected for watershed size so that we can compare the different watersheds. And this is, I'll show you how we did it. I'm going to show you an example watershed. This is the Cottonwood River near New Ulm. This is the flow record 1940 to present. Here is the trend in annual water yield or flow. And there is a significant increase. We evaluate these, and this says that this trend, the fact is, for this river, we are 99.9% certain that the flow has increased over this time period. And there are a number of ways to evaluate what the magnitude of that change is. To be on the conservative side, we did not simply compare the endpoints. We said, let's take the flow over this whole period and compare it to the flow over this whole period. This line simply divides the data set in half. There's nothing magical about 1975. It's half of the data set. So we're comparing the period 1940 to 1975 with the period 1976 to 2009. And the median or mean, if you want to think of it, flow has increased by 75%. So between these two time periods, we are 99% certain that flow has increased by 75%. That's a big number. We did that for all 21 watersheds, and this is what we see. The red bars represent watersheds where the flow has increased and the flow is statistically significant. The blue, I'm showing those, that's the increase that we observe in those rivers, but it's not statistically significant, and it's appropriate to say these flows have not changed. There's two important things that show up here. One is that the changes are not random. in flow. If it was simply climate or even urbanization, we would see a more random distribution of how these flows have changed. And it's important, very important, that some watersheds have not changed. That's an equally important finding here, because if it was simply climate as the driver, all of the watersheds should have shown some statistical change, and they don't. So we already have our first inclination that we're not going to be able to tie all of this just to climate. And by climate, I mean precipitation. I'm not talking global warming, I'm just talking precipitation in general. So now we need to really think about how rainfall is a driver of flow. And there have been some studies published saying that flow increases are strongly correlated with changes in rainfall. As rainfall has gone up, flow has gone up. So we looked for that in our watersheds, and we said, what if we simply plot flow as a function of precip? And I'm going to plot it a little differently here. I'm going to plot cumulative precip starting in 1940 through present, and cumulative flow starting in 1940 through present. So I take 1940's precip, I add it to 1941, to 1942, 1943, all the way through, and the same with flow. And the reason we do it that way is we take care of antecedent conditions. If there's a wet period that makes the next year that's actually dry still have high flow, this is carried through in it. So it's the total amount of flow and the total amount of precip over this time period. And if precip is the driver of flow, there should be a nice straight line through this saying that as we get more precip, we get more flow. And that's exactly what we see here. As precip increases, flow increases. Rains more, you get more flow. The cumulative approach takes for antecedent condition. This is a strong correlation. But are we sure? Because remember, I already hinted to you that we got some evidence that it can't quite be Mr. Thompson. Is that Tony? I have an old friend, I haven't seen him in a while. That we already have an implication that it probably can't be all precipitation. So let's look at this in a different way. Let's think instead about corn planted versus corn harvested and a regression. This is the data right off of the NASS website, National Agricultural Statistics. Millions of acres of corn planted, millions of bushels of corn harvested 1960 through 2010. As we plant more acres, we harvest more acres of corn and corn yield. So nice linear trend, relationship is linear. So our interpretation would be there's been no change in the yield of corn. That's what the slope of this line is. This is bushels per acre. Plant more, get more, and that relationship is proportional and constant over time. Is that correct? No. What if we split, we know corn yield's gone up. What if we simply split this data set in half? Just right in half. 1960, 1985, 1986, 2010. That's what we see. I took that same linear regression and I just split the data in half, and now you can clearly see this is the amount harvested yield per acres planted 1960, 1985, and this is the amount now. The slope of this line is much greater than the slope of this line. This represents a yield of, I think it's 65 bushels to the acre, and this is 135 bushels to the acre. There's a danger in interpreting linear relationships without thinking about them more. This linear relationship that I previously showed you, I'll give you a very quick lesson in statistics about how to read this. This R squared value, that says 97.6% of the change in flow can be described by the change in precipitation. That is a phenomenally good R squared value. But look what happens when we split the data set in half. Same data, 1940, 1975, 1976, 2009. There are two different slopes here. I did the same thing with this data set that I did with corn yields to look at how the relationship changes over time. It gets steeper. This slope is about half of what this slope is. If precipitation were the sole driver of changes in flow, we should have followed this line through the rest of time, this dotted line. But this line increases. And in fact, there's not two lines here, there's a curve doing this. This difference right here is the increase in flow above and beyond which can be described by the increase in precipitation. The answer is that precipitation is the driver of flow. If it doesn't rain, the rivers will dry up. And when it rains more, the rivers have more flow in them. What has changed over time is the proportionality between precip and flow. An inch of rain now generates more flow than an inch of rain in the past. It's that proportionality, and that is very apparent in here. This is simply measured data and a relationship. This period of time is clearly more flow per unit precip than this time. We can't deny that part. We get to interpret how this is, but we can't deny what's going on here. This relationship between flow and precip, flow divided by precip, is a term called runoff ratio. Runoff meaning all the flow in the river, whether it came from overland or groundwater. Oh, I guess it's the next slide. But also to show you is that some rivers, this relationship is linear over time. It does not change. An inch of rain in the Rum River watershed generates the same flow today as it did in the past. It generates about twice the amount of flow in the Cottonwood River as it did in the past. And this runoff ratio, this is the change percent-wise in the change in runoff ratio for all of these watersheds. And what you see is there's some numbers here that are above 100%. What that means is that flow has basically more than doubled per unit precip over the period 1940 to present. Over the last 70 years, more flow per unit precip. Okay, so rainfall is probably a partial driver of the changes in flow, the proportionality. But what else has changed? What else can we use to describe why has this flow changed disproportionately? And one of the things that's often brought up is rainfall intensity. Well, maybe it isn't that we're getting more rain, but we're getting rain in a more intense fashion. We kind of assumed it would be, and we were surprised by the results. And this is work by Jason Ulrich, here who's sitting in the front row. And I'll just give you one example. This is the frequency of 1 inch per hour rain events, 1948 to 2009. We have a little different data set for the rain than the flow numbers. 1 inch per hour rain events have not increased over the last 65 years. And the fact is, the blue triangles are those that show a decreasing trend, and the red are the increasing. There are more blue triangles than red triangles. If anything, if we operated in a vacuum, we'd say, well, maybe rainfall intensity is actually decreasing. Almost none of these trends, up or down, are significant. The main conclusion that we can draw is that rainfall intensity is not changing. And I don't want to get into an argument with any climate scientists and other data talking about rainfall intensity, because there are other studies that show rainfall intensity changing in other parts of the country. And it's also possible that rainfall intensity is changing here, but that it's just beginning and we haven't observed it yet, and that maybe there are some changes, but they are very small at this time. The point for us is not whether or not climate change is causing changes in rainfall intensity. The point is that whatever changes in rainfall intensity have or have not occurred are not large enough to be factors in changes in flow. And that's what we're interested in, is what's causing flow to change, and there's just simply no way we can link it to rainfall intensity because it's not there. Okay, so what else has changed? And this is data from Rick Moore. This is the change in cropping patterns in Minnesota. And here we've combined all of the watersheds, and I hope that shows up okay. But this is 1920 to 2009, and what you see is that corn bounces along at almost the same rate of planted acres over time. But what really changes is soybeans and oats, wheat, barley, alfalfa, and small grains. In 1940, on my grandpa's farm in Mower County, Minnesota, they didn't plant soybeans. They didn't plant soybeans until 1952, I think Dad said. And that trend is the same for the state of Minnesota. Soybeans were not really a crop until the 1940s, and now, as we know, they're almost 50% of the cropped acres. And what has happened is that we have replaced hay, alfalfa, and small grains with soybeans. The corn acres are about the same. And that's an important change. And in fact, that change in soybeans acres is strongly correlated with the change in flow. 80% of the change in flow is described by the increase in soybeans. 80% of the increase in flow is correlated with the change in soybeans. And the reason this is important, if we'll look at the seasonal changes now, because everything I presented so far is our annual changes, is even, I think, is more evident. This is if we put all the watersheds together, this is the change in flow and precip just for the months of May and June. May and June is when we have the largest increase in flow, and very surprisingly, we don't have an increase in precip in May and June. The increase in rainfall that's occurred in Minnesota, first of all, the largest increase is about 8%. It's not a big increase. And it's in the summer and the fall. May and June are actually drier now. Well, May and June are the same now as they've been in the past. If you plot this, this isn't really a statistical change. And this is important because 40% of the annual sediment load is during the months of just May and June. This is where this crop conversion is important because in the past, in May, we had alfalfa fields that were green and growing, almost ready for their first cutting. They're using up lots of water. 70% of these alfalfa, hay, small grains have been converted to soybeans, and they're just getting growing, and they're not using much water yet. So that change in cropping patterns has the potential to change water use and therefore runoff. And what I'm showing you here is that the largest increases in flow are occurring at a time of year where the water used by crops has actually decreased. And I suspect there'll be questions at the end about the change in leaf area index and cropping, and I'll bring this up again, but we can't run away from this conclusion that we simply don't have the ability to use up a lot of water in the cropping patterns in May and June now because we've replaced the things that are using water with things that aren't using water. Okay, and the other thing that changes over time is artificial drainage. It might be a little hard to read there, but you can see this here. It's underground, it's extensive, it's increasing. I show this slide often to more urban audiences who are completely unaware of the underground hydrology in our agricultural landscapes. I probably don't need to show you guys this, and the percent of land tiled is also strongly correlated with the change in flow. 53% of the change in flow can be described by the percent of land tile drained. I use the word tile here, substitute artificial drainage there, with the amount of artificial drainage on the landscape. And it's often brought up, what about population increase in impervious surface area? This is the relationship of flow, and here I'll plot runoff ratio, to change in population density. And what you see, if anything, there's a decreasing trend. And this is because the places where flow is monitored, for example, on the Blue Earth and the Seward River, is upstream. It's before Mankato. All the sites that we picked are above their major population centers. So while these population centers may have increased flow downstream, at the places where we're measuring and evaluating flow, we cannot implicate the population centers. They simply, if anything, it's a decreasing trend. It's non-significant. So all these things have changed and are correlated. Population can't be related to flow increases. Cropping patterns of conversion to soy is correlated to water yield. Artificial drainage is correlated to water yield. And there's one more. This is the same period of time, 1930 through the 2000s. Very strong relationship. 81% of this change is described by, the percent of land in soybeans explains 80% of the losing percentage of golden gopher football. So golden gopher football is also strongly related to the change in soybeans. And that's because correlation is not cause and effect. There are a lot of things that are correlated to the change in flow. Some are mechanistically related, like the ones I showed you, but we can't separate cause and effect by simply looking at correlations, especially because precipitation increases, conversion to soy, and drainage all increase over the same period of time and all have the potential to change flow in the same direction. So how do we separate these? We're going to have to do math. We're going to have to do math on some things that we don't often think about. And that's evapotranspiration. Precipitation and flow, which I've looked at already, are measured. And I think we understand those well. But evapotranspiration is the larger part of this story. It's the biggest part of this story. It's invisible. It happens when we're not watching it. And it's 70 to 80% of our water budget in the state of Minnesota. 70 to 80% of the rain that falls on the landscape is returned back to the atmosphere either as evaporation due to solar radiation or use by crops through transpiration. If we're going to figure out why flow has changed, we're going to have to look at evapotranspiration. And crop conversion and drainage and precipitation all have the ability to change evapotranspiration. When you rain more, you can also ET more. So this is our water budget. Flow, Q, precip, P, ET. That's our supply of water. This is our demand for water. And this is what's left in our bank account. That's all this is. Little simple bank account. Both of these parameters are measured. Measured, not modeled. We know those. This one is not measured, and it's very difficult to get a handle on. And it's a function of a variety of things: solar radiation, crop type, residence time in the landscape, and it's a function of precip, which means you cannot simply go and solve this, take Q minus P and say, oh, I got my ET. ET is not just one thing because it's a function of each of these. So we're going to split the water budget into flow is precip. There's an amount of evapotranspiration that's caused by climate. It's just solar radiation. Is this year hotter than last year? The crop. Alfalfa ETs more water in May than does soybeans. And then there's ET other. Oops. And this other, in our landscape, is largely driven by drainage. There's a certain amount of evapotranspiration that we get by residence time. The longer the water stays in the field, the more we can evaporate it. To solve this is tricky because that last term isn't measured. The others are modeled. And they're each a function of a variety of parameters. And we struggled with this for a long time. And I put this up not to expect you to understand it, but to show you that we looked at it in a way that is mathematical, dealing with the measured numbers in a way that we can replicate for each of the watersheds. And we simply said water yield or flow is a function of ET and precipitation from the cropping patterns, precipitation, the measured parameters. And this is the relationship. And you notice it's not linear, because a lot of you will point out and say, well, when I get a 3-inch rainfall, I get a whole lot more runoff than I do when I get a 1-inch rainfall. Yep, that's why this gets steeper right here. And this is why it gets flat. These are those little 1/4-inch rainfalls down here. These are those 3- and 4-inch rainfalls up here. We've got that nonlinear problem taken care of. And because we're putting all the years together here, we've taken care of some antecedent conditions. There are points that lie above this line. That's because those are wet years, followed by wet years. The points below the line, those are dry years, followed by dry years. This is for the first time period. If nothing has changed, then this relationship will be the same for the second time period. And it's not. When we look at how this has changed over time, and we solve it, and again, I don't expect you to follow this, but I'm trying to point out that we've done this in a credible and replicatable fashion. This right here, this is the flow change that's due simply to the change in cropping patterns and precip. So there is a change due to increased rainfall and the changes in cropping patterns, and it's this amount here. The remainder is the amount due to drainage. And when we solve that then for all the 21 watersheds and apportion to rainfall, crop conversion, and drainage, this is what we get. The brown is the amount of flow increase due to drainage, and you can see that it's more than 50% in most of the watersheds. And crop conversion turns out to be fairly small on an annual basis, and the remainder, 1/3 to 1/2, is due to rainfall. So rainfall is a driver and is calculable in terms of our increase in flow, but more of the change, the majority, more than 50%, is due to artificial drainage. Artificial drainage has increased flow in our rivers. There is uncertainty about these bars and the magnitude, but the direction I think I can show you is unequivocal. And that's because it's all about water residence time. Artificial drainage reduces water residence time on the landscape. A landscape that is wet, holding water for a long time, can't get the tractor into it, soggy soils, crops won't grow, we drain that quickly. That water used to sit there. Some of it would infiltrate, some of it would evaporate. Now essentially it all infiltrates. That's what the drainage is doing. It's taking that water away quickly. So the proportion of water that used to get to evaporate is now routed directly to the rivers. Water that used to evaporate is now routed to the rivers. That's what drainage does. That's the concluding statement, really. And in fact, we can go further and show that, in fact, we can show evidence to link this. Rick calculated the loss of depressional areas. So this is more than just wetlands. These are areas that hold water for some period of time. They're the exact places that we're putting drainage into. And these numbers are the percent of the landscape that was depressional and is now drained. So you take the greater Blue Earth and Le Sueur watersheds here. 15 to 20% of the entire watershed area was depressional holding water and is now drained. 15 to 20% of the watershed now has a much shorter residence time than it did in the past. And we can relate this amount of drained depressional areas to the change in flow. The more depressions that have been drained as a percent of the watershed area, the greater the increase in flow. The more of your watershed that you've short-circuited that water residence time and routed the water to the rivers, the greater the increase in flow. And it's strongly linked to the amount of depressional areas. And this is an important reason of why I separate and say we talk about artificial drainage, because a lot of artificial drainage is put on the landscape to drain depressional areas. But tiling is put on the landscape both to drain depressional areas and sometimes non-depressional areas. So I'm not trying to single out and say tiling itself is bad in terms of changing flow. What I'm saying is, if you want to actually substitute in the word for tiling, tiling has an effect on drainage, tiling has an effect on flow when it shortens water residence time in an area. To the extent that it does that, it's changing flow. And here's the consequence of this. How much time do I have, by the way? Okay. This increase in flow has had a consequence. It's causing our river channels to widen. This is the Blue Earth River in 1939. This is the Blue Earth River today. Oh, the yellow line barely shows there. Rivers like the Blue Earth, the Le Sueur, the main stem of the Minnesota River, are 15 to 40% wider now than they were in the past. This widening is a source of sediment. When you widen, you take those banks down, poof, they're in the water. The fine-grained particles stay in suspension and work their way through, making the picture like we saw in the first one with the St. Croix River and the Mississippi River. And in fact, this increase in channel width is strongly related to the increase in annual water yield. As the rivers that have increased their flow more have had more channel widening, and we're continuing to work on this with more watersheds and greater extent to the watersheds. When we put this all together, it's telling us that this increase in flow is not just more water, it's more water, therefore more energy, channel widening, more suspended sediment, greater turbidity, reflected in the Lake Pepin sediment record, where we're showing that the proportion of sediment from non-field sources, stream banks, has increased 5-fold over time. This is the story of why that 5-fold increase in Pepin has been observed. And the majority of it, but not all of it, is linked to artificial drainage. This practice of artificial drainage has been occurring certainly prior to 1940. We have less data before that time period. One of the best pieces of data that we have is the 7 Mile Creek watershed. This was put together by Kevin Keener, and then Rick Moore re-summarized it. 7 Mile Creek watershed just upstream of Mankato. He put together the loss of wetlands. These are the big depressions, not just the little depressions, for all time. And you see that the watershed was, I think it was 70% wetland at the time of settlement. You go through time, almost all of it is gone. So we know the trend in wetland loss for 7 Mile Creek watershed. And that watershed is probably pretty typical of most of the Minnesota River, most of the lower and middle Minnesota River basin. So this is the wetland loss trend in 7 Mile Creek, pre-settlement to the current. And I'm going to pull in a variety of data here to tell a summary story. This is the change in runoff ratio 1940 to present for 3 rivers that are, these 3 rivers load an awful lot of the sediment load. The Blue Earth and Le Sueur combined are somewhere between 30 to 45% of all the sediment load. And here I smoothed out the data just to make it easy to read, but this is the change in flow. Here I normalized it to precip to get rid of the proportion that's precip. This is the increase in flow in these three rivers. This is the change in wetlands. This is the channel widening that's been measured over time of the Minnesota River main stem at Jordan. And this is the Lake Pepin sediment accumulation rate. I want to put all of these up together to sort of link this story. This is what it looks like if we take those last four trends and superimpose them on one another in a time trend. We drain the wetlands with this red curve. Flow in the rivers increases. Channel widening, therefore putting more energy in the river. Channel widening occurs, and the Lake Pepin non-field sediment accumulation rate goes up. While these are correlative, and I showed that, Mr. Gorefer, correlation is not cause and effect, this is supporting evidence that the story fits together about how our alterations on the landscape have changed the suspended sediment and turbidity loads observed throughout the watershed over time. We have to do more work on that. And then that brings us then to the Kensington runestone, real or not real. So after seeing all of this information on drainage, how many of you now think that the Kensington runestone is real? Raise your hands. That's it? Because you're wrong. It's real. The Kensington runestone is unequivocally real. I touched it. The stone is real. The carvings are real. Those are actual runic carvings on there. They're real. It's the interpretation of who carved them that's in doubt. The current evidence favors Ulf Ullman, but it has not been proven. I work with a scientist who says, it's not real. And I said, you can't prove it. You can't prove it. It has not been proven that it's real or fake. And the same is true for flow, suspended sediment, and precip. The changes in flow are real and measured. We can't, that's the best data we have. We can't do any different. Our flow has increased. Our flow has increased by more than precipitation has. And the records that we have of suspended sediment, while limited, are also real, showing an increase. We cannot deny those parts. They are equivalent to the stone and the carvings. It's the interpretation of what's causing them to change that is in doubt or is questioned. I presented to you today our interpretation of why flow has increased in the rivers and what the drivers are and the parts that it contributes to each of those. And that interpretation certainly can have further scrutiny and data gathered. That's the same as the stone. But the parts that flow and sediment have increased are definitely real. Our evidence says that more than 50% of the increase in flow can be attributed to artificial drainage. And our interpretation is supported by solid evidence. And I would ask those of you, particularly those who might be skeptics of some of this, is to show me where in this sequence that you don't agree. We put drainage on the landscape to get rid of water quickly. And it works, right? If it didn't work, we wouldn't keep putting it on the landscape. But that's why we put it there. Therefore, we are changing water residence time on the landscape. When you shorten water residence time, less water gets to evaporate. What happened to the water that used to evaporate and now doesn't? It's routed to the rivers, therefore increasing stream flow. More stream flow has more energy, which is going to create more erosive rivers. When you widen the channel banks, that sediment ends up in the rivers and ends up as suspended sediment. This story, I think, fits together pretty neatly and is pretty tight. Whether or not the drainage is causing a 50% increase in the flow, a 30 or a 90, and by the way, I can show you data where we would say it's 90% of the increase, is the part that deserves further scrutiny. But the question as to which direction drainage is changing flow, I think, is pretty undeniable. And this is important because, like the rune stone, there will be a response to our interpretation. Management decisions will be made based on what we have decided is driving changes in flow. And those that response to interpretation is important. Do you know what the response to the interpretation that the runestone is real is? You know what the response to that is? That's why we're the Minnesota Vikings. Our football team is the Minnesota Vikings because the interpretation that the runestone was carved by Vikings is accepted. And so that's a big deal. We got an NFL team that's worth a lot of money that is a response to an interpretation that perhaps is faulty. Management needs to be based on reality. Science's job is to describe reality. And that was all I was here today to try and do, was show you the data that we have based on measured observations and the interpretation from that data. Thank you. Do we have time?
Yeah. We do have about 10 minutes. I'm a stickler for time. So we do have about 10 minutes for questions. I've gotten a lot of really good ones from you guys so far. Mark, wherever he went, you get to be the dude that collects the questions now that I'm up here with Sean. And I'm going to just read some off because there are a couple duplicates, so we're going to start with those. And then as time allows, we'll continue with the rest of them. So we had a number of people that asked about, in general, the widening of the rivers. Some folks just questioned when, timescale-wise, our rivers will kind of slow down or quit widening. Others have asked if that or when that happens, will that increase or finally decrease the amount of sediment that's going into Lake Pepin? At the same type of thing, when we've kind of slowed way down with artificial drainage, is that going to slow the widening type thing? So that's kind of our general river widening questions.
That's an excellent question. We ask it ourselves, when will this level off? And remember that first slide was about real versus speculation? And what I'm going to present now is speculation, okay? So keep it in that context, this is speculation. At some point in time, when flow no longer increases, the channels will widen to the point that they are now stable, and they will no longer increase in suspended sediment load. So, and that's going to happen. It happened in the past. There's been times, talking over the last 10,000 years, where we've had wet and dry climates and the rivers have adjusted accordingly. In fact is, the main stem of the Minnesota River channel, if you drive and you look across the Minnesota River basin, you notice how it's just really, really wide. That's because there used to be a really, really huge river flowing through there, Glacial River Warren, when Glacial Lake Agassiz drained. And now the system, of course, doesn't widen like that anymore because there's much less water. The question is when will it happen? And there are a number of colleagues, geomorphologists, who work on this, and there's a debate that it could be a long time, or it may have already started. You notice I showed you on that Lake Pepin graph that the last decade is a little bit less than the previous decade. We could say that maybe we're already starting to see, I also have some suspended sediment records, that on the large scale, because basins like the Blue Earth and the Waseca rivers, those are the first basins to get heavy drainage, and they're getting less and less now, but those are also the basins with the largest sediment contributions. Maybe they're already starting to tail off. Don't know. The other thing that weighs into that question is what will the new normal be? Just because we stop channel widening doesn't mean that the suspended sediment load will go back to what it was previously, because we also have bluffs in these systems. And bluffs erode differently than stream banks, and so almost certainly the new normal sediment load is going to be larger than what it was prior to these large flow increases. So there's two parts to that question. When will it level off, and what will the new normal be? And we don't know, but we are doing some studies on that. We're going to be looking at it. And the other thing to keep in mind is, in the future, we're going to be interpreting suspended sediment turbidity records from the river. And we got to keep that in mind, that if we see downward trends, do we interpret that as the channel widening has stopped, or that no-till farming is working, or the buffer strips are working? That's another one of those coincident and confounded things that are happening at the same time. So stay tuned on that question.
Okay, the next one. When comparing change in flow across watersheds, How did you account for varying rates of infiltration to the groundwater across those same watersheds?
Infiltration and surface runoff are both the things that contribute and make flow. So flow in the river is a result of both infiltration and surface runoff. I think sometimes, I think about how my mom thinks about these. My mom thinks that any water that falls in the ground and goes into groundwater goes into her well, 280 feet deep. Very little of it does, but even the water in her well ultimately ends up in this, where we are in the St. Croix River. So it's accounted for because that is what the flow measurement is. Flow is the combination, the addition of infiltration plus surface runoff. So it's accounted for because they're both in that number. I suspect that whoever asked that question has a follow-up question, but you can catch me in the hall.
Next question. What about urban development? How is that relating to the flow that we're seeing?
A good question, but again, for the watersheds that I showed you here, we simply cannot link any change, and if we tried to, it would be negative in terms of flow to population, because the places that we've measured flow in these watersheds at their outlets just have not had big population growth. The big population growth in the state of Minnesota is St. Cloud, Duluth, and Minneapolis, St. Paul, and those aren't the rivers that are having the channel widening. But I can also tell you that when we look at flow and suspended sediment records as it flows through Minneapolis, St. Paul, it decreases. So urbanization, while it definitely has effects on our whole water budget, is not linked to increases in flow. It's not linked to increases in sediment. I mean, again, it's a runestone thing. You can go look at the real measured data, and you look at the numbers up at Coon Rapids Dam and then again at Red Wing, and we've got a small decrease in the suspended sediment load, not an increase. But on that, urbanization has its own set of problems and water quality degradants. It's just suspended sediment doesn't happen to be one of them in this case.
All right, we have a few more here. This one. Understanding the infield sediment outflow has increased. What can also be done to curb the increase in the in-stream sediment flow? How banks, sloughs, etc.?
Well, there are people in this room like Al Kane who this is their job, is to try to answer that question. But also I'll just answer it very broadly. From what our study can be used to say is, at some point we have to simply decrease flow volumes. Particularly, and I won't go up to the slide, but we have to decrease infiltration and surface runoff that contributes to bank full flow volumes, which is where the erosion is probably taking place. The other thing to think about on flow, beyond the sediment talk that I gave you here, is that land use, crop conversions, and drainage have a story also regarding phosphorus and nitrogen. And the role of artificial drainage, and particularly pattern tiling, to nitrogen loads is a very significant story, and one that I think we need to be considering how we're going to manage, above and beyond just the sediment question.
This one we have a question about kind of the frozen period, our winter period in river depth. So in January, the Minnesota River at Mankato was roughly 1 foot in depth. By the middle of March, the Minnesota River was over 5 feet. The artificial tile were not running at this time. What do you feel is the explanation for the rise in the river?
When did it rise again?
March, basically, just lately.
I'm not sure. That's a single year's observation with all kinds of soil moisture, frost depth, snow depth questions, and without looking at those, I really couldn't say. Do you have an idea? That's a single point observation time that, with looking at the data, I think there's some interpretations made by it. I'm not equipped to answer that at this time.
And our last one that I have, if your research is correct, what would you propose as a solution to this issue?
What do you mean, if our research is correct? that more subsurface perforated black tile is the problem. It might be, and it might be that when you go from 40-foot spacings to 20-foot spacings, the amount of additional water is not increased significantly. And it also might be increased significantly. We don't have those numbers at this time on a watershed scale. The only part that we can say for sure is that when we drain depressional areas, things that held water for 3 weeks and now hold it for 3 days, that's definitely contributing to it. So we certainly should not drain any more wetlands, which for the most part we're not. But I can tell you that in the Dakotas, that's not the answer. It's happening there. And there's also a conversion from small grains, grass, hay, even native prairie, to soybeans. So the first thing I would say is let's not repeat some of the same mistakes we've made in the past. But beyond that, we're not going to stop pattern tiling. Its role in agriculture is too great, too embedded, economic value is large. And the question is, how are we going to manage it relative to sediment, and I think even more difficultly relative to nitrogen. And I don't have the answers for that. It's a very difficult situation that we're in.
Well, that concludes the questions that everybody had, and we're on time, which makes me happy. So let's give Sean another nice thank you.